Polarimetry. A polarimeter is a device used to measure the optical activity of a given solution. If you have a source of light and a beam of light through that source of light passes through a polarizer, the polarizer is going to polarize the beam of light into a single ray, right? Into a kind of a single ray. So if you have that single ray to pass through a solution that is optically inactive, then the rays will pass through it straight forward without no change in angle. So this is a solution that is optically inactive. So if the polarized light passes through the solution and did not change in angle, then the solution is optically inactive. Now, if the polarized light passes through an optical active solution, there's going to be change in angle. As you can see, as the ray goes through it, the more it goes, the more it deflects. I mean, it creates an angle. So you could see that we have an angle here. We can call it alpha. So if you are given a solution and you pass a polarized beam of light through the solution, the beam of light may form an angle or turning to the right hand side, or form an angle turning to the left hand side. To the right hand side, we call it dextrorotatory. If the solution turns, if the beam of light form an angle to the right, it is called dextrorotatory. And it is usually indicated by clouds. If it turns it to the left hand side, which is counterclockwise, it is level rotatory. Level rotatory, usually indicated by the minus sign. So depending on the nature of the solution, it will turn to the left or the right. To the right is dextrorotatory, and to the left is level rotatory. So that is how the polarimeter works. If you pass a beam of polarized light into a chiral solution, the beam of light, is going to form an angle either to the right or to the left, depending on the rotation, depending on the nature of the solution. Previously, we made mention of enantiomers because this solution is going to contain its enantiomers. Let's say, assuming the R and the S enantiomers. So depending on which of these dominates, if the R dominates, let's say the S should be positive. If the S dominates, then it will give us dextro. If the R dominates, then it will give us level. Notice that S is not always dextro. I'm just using this for illustration sake. So the one who dominates will rotate the more angle. If R is more, then it's going to rotate to the right more. If S is more, it's going to rotate to the left more than the R. Sorry. The one that dominates the solution is going to create more angle. This angle here, we call it observed rotation. The angle T alpha here is the observed rotation. The formula used for calculating optical purity is where is the specific rotation. And the alpha here that we talked about is the observed rotation. All the angles are measured in degrees. And temperature, T is temperature. In degrees Celsius. C is concentration. In gram per milliliters. L is the path length. And is measured in decimeter. The path length is usually the length through which the polarized light passes through the solution. Lambda is the wavelength of the light source that we are using. Usually, generally, we use sodium D line. We use D line sodium. D line sodium as our light source. So this place can be represented by D, and we use that light source at 25 degrees Celsius. 25 degrees Celsius. That is our temperature. So the formula, this formula right here, can just be written in simple form as the observed rotation over path length multiplied by concentration. One thing I need you to know is that if the polarized light passes through the solution and there is no rotation, that is not a guarantee that the solution is optically inactive. The solution might form a racemic mixture. In a case where we have the R turning it to the right and the S turning it to the left, in a case that we have 50% of the R, let's say S, and 50% of the R, it means that there's not going to be rotation, right? Yeah, practically, which makes sense. So in this case, as a chemist or physics, the polarimeter cannot tell you whether the solution is racemic or optically inactive by telling you directly. So once there is a rotation, you can say something about it. Once there is no rotation, you can go on to perform a further experiment to determine whether your solution was it racemic or the solution is achiral. The experiments that you can further perform can be the evaporation method, the chiral solvent addition method, or the high performance liquid chromatography method. So now that we are here, let's look at some practice problems. 0.6 grams of chiral stereoisomer was dissolved in 30 ml of solution. The observed rotation measured by a polarimeter was found to be -3 degrees at 25 degrees Celsius using a wavelength of 589 nanometer. The sample tube of the polarimeter is 20 centimeters long. Calculate the SR, which is the specific rotation of the stereoisomer. Solution. Let's try putting our parameters together. We have 0.6 grams. We have mass, which is 0.6 grams, was dissolved in 30 ml. And we have a volume given to be 30 ml. The observed rotation measured by the polarimeter, and we know that observed rotation is alpha. which is minus 3 degrees. At 25 degrees using wavelength of 589. This wavelength is a wavelength of sodium D line, the D line. So it is not of use for us, but the condition should be there to guide us, because the wavelength is not included in the formula that we just derived. So the sample tip of the polarimeter is 20 centimeters long. So that should be our L is 20 centimeters. Are there some conventions that we need to make? So 10 centimeters equal 1 decimeters, and 1 centimeter equal 10 millimeters. We should know this convention. The formula for the calculation, we have to calculate the specific rotation. Specific rotation, 25 degrees Celsius, D line, you can indicate the 589 here, nanometers, equal observed rotation over concentration multiplied by path length. Now, we have the observed rotation here. We don't know the concentration. And concentration can be mass over volume. This is the relation, the formula for concentration. So we have the mass to be 0.6 grams over volume, which is 30 ml. This will give us 0.02 grams per milliliters. Mind you, our concentration should be in grams per milliliters. Then that is okay. Our path length should be in decimeters, dm. And we know that 10 centimeters equal 1 decimeter. So 20 centimeters will give us 2 decimeters into bracket 2 dm, decimeters. So now that we know our specific rotation in degrees, our concentration in gram per milliliter, and our length in decimeter, we can do substitution. So minus 3 over concentration, so okay, length multiplied by concentration, 0.02 grams per liters. The length is in decimeters, sorry. So this will give us minus 75 degrees. That is our answer for this problem. And what does minus 75 degrees specific rotation means? What is it telling us? It means that the polarized, beam of light passed through the solution and it turned to the left at 75 degrees. So the left level is indicated by negative. So it turned to the left at an angle of 75 degrees. A pure sample of naturally occurring chiral compound A of mass 0.050 gram is dissolved in water of volume 2.0 ml, and the solution is placed in the 0.5 decimeter cell. 3 polarimetry readings were recorded with the sample. So 0.625, 0.706, and 0.682. What is the specific rotation of this compound A? So the student was analyzing this solution. He decided to perform the experiment twice, taking 3 observed rotations. So first of all, we need to calculate. Before that, let's see the parameters that we were given. So we have the mass of the solution, which is 0.050 grams. And we have the volume, which is 2.0 ml. and we have the length for the path length to be 0.5 decimeters. So the given polarimetry readings, I mean the observed rotations that were recorded in the experiment are these. So we want to calculate for the specific rotation of this solution. And specific rotation equal observed rotation over concentration multiplied by path length. Now we have three observed rotations. We can calculate for the concentration using mass and volume. So concentration equals mass, which is 0.050 grams over 2.0 ml. And this is going to give us 0.025 grams per ml. So we now have our concentration, but we don't have our observed rotation. Since the student performed the experiment twice, or since this experiment was performed twice, we find the average of these observed rotations. So it's going to be 0.625 degrees plus 0.706 degrees plus 0.682 degrees. The experiment was performed 3 times, so divided by 3. That is why we have 3 observed rotations. So this will give us 0.671 degrees. That is the average observed rotation. So now we can continue with our calculation. 0. And it is positive. 671 degrees divided by concentration, which is 0.025 grams per ml, multiplied by path length, which is 0.5 decimeters. So this one will give us positive 53.68 degrees. That is the specific rotation for the chiral compound A. 1.20 gram of methanol is dissolved in 5.0 ml of ether and placed in a sample cell 10.0 centimeters in length. The observed rotation at 25 degrees Celsius using D line of sodium is plus 0.58. Calculate the specific rotation of methanol. Solution. Mass is given. We have mass given to be 1.20 grams. And we have volume given to be 5.0 ml. And we have L given to be 10.0 centimeters, which is 1 decimeters. If we convert it to decimeters. And then we have observed rotation given to be plus 0.58 degrees. Now we need to calculate for our concentration. C equal M over V, which equal to 1.20 grams over V, which is 5.0 ml. This gives us 0.24 grams per ml. And our specific rotation at 25 degrees Celsius using the D line sodium equal observed rotation over concentration multiplied by path length. We know the observed rotation to be plus 0.58, so just 0.58 degrees, and concentration to be 0.24 grams per ml, and the path length to be 1 decimeter, so multiply by 1 dm. So this is going to give us a positive 2.416 degrees. That is the angle that we get for the specific rotation, and it is positive. It means that our sample rotated the plane polarized light to the right dextro at 2 0.416 degrees. A student attempts to separate R and S to butanol. The final solution is 0.25 gram per ml at 25 degrees Celsius. Was the student successful if a 10 centimeter shell show a minus 2.5 rotation using D-line sodium, given that specific rotation of the D-line sodium at 25 degrees is minus 13.52 for the R configuration, for the R enantiomer. So it means that the student has a solution which contains both R and S enantiomer, and the student was interested to separate the enantiomers. Specific rotation tell us the ability of a solution to rotate plane polarized light. And most chiral solution, or almost any given chiral solution, has a specific rotation. In this case, we have been given a specific rotation, right, for the solution. And the student already performed the experiment and already had his observed rotation to be minus 2.5. So we are going to calculate for the observed rotation with the given specific rotation and the parameters. After that, we compare to the observed rotation of the student to see whether he was able to separate the enantiomers. So now we are giving concentration to be 0.25 gram per ml. Specific rotation known, and then the length, the path length is 10 centimeters, which is 1 dm, 1 decimeters. I'll equal to 1 decimeter. So now we have specific rotation to be equal to observed rotation over concentration multiplied by path length. Now we know the concentration, we know the path length, and we have the specific rotation of the solution given. What we are going to do is to calculate for the observed rotation and compare it to the observed rotation that the student had to see whether he was right. So making observed rotation the subject gives us specific rotation multiplied by concentration multiplied by path length, which is going to give us 13.52 minus 13.52 multiplied by concentration, which is 0.25 gram per ml multiplied by 1 dm, 1 decimeter. So this is going to give us minus 3.38. This is the ideal observed rotation. The ideal observed rotation that will give you this specific rotation. But the student had his observed rotation to be minus 2.5. Let me take that again. The student is interested in separating the R enantiomer from the S enantiomer of 2-butanol. And he had an observed rotation to be minus 2.5. But to separate completely the R enantiomer of 2-butanol, your specific rotation should be minus 13.52, right? So we have to calculate the observed rotation, and we had the observed rotation, ideal of the observed rotation, to be minus 3.38. But the student has his observed rotation to be minus 2.5, which means that the student should have gotten this observed rotation because he wants to separate totally the R enantiomer from the S enantiomer. And because the observed rotation, the ideal rotation, observed rotation is different from the student's own, it means that some of the R enantiomers are still in the solution. they were not completely separated. So the students observed rotation minus 2.5 is kind of fake with this specific rotation, because this should be the observed rotation. Enantiomeric excess or percentage purity, you can say enantiomeric excess or percentage purity, or it's about the same thing. Now in a solution, this is calculated in percentage. In a solution, if I mean, in an optical active solution, if I have R and S enantiomers in the solution, let's say as the S enantiomer is turning the polarized light to the right, the R enantiomer would be turning the polarized light to the left, right? As one is turning it to dextrorotatory, the other is turning it to level rotatory. That is class. So if I have 50 of R and 50 of S, as S is turning it to the right, R will be turning it to the left. This is just a general term. It is not to say the S is always dextro or the L is always level rotatory. So because we have 50-50 of both enantiomers, there would not be an angle, right? Which means the solution will be a racemic mixture of R and S. What if I have 70 of R and 30 of S? What happens? So it means that as 30 is pulling to the right, 70 will be pulling to the left. So at the end of the day, 30 of the R will form a racemic mixture with this, 30 of the S. So it means that if 30 form a racemic mixture, then we will still have some of the R in the solution, which will be 40 of the R in the solution. So at the end of the day, the R will dominate and it will turn the plane polarized light to the left. In this case, we are assuming that R will turn to the left and S will turn to the right. So it will turn to the left because R dominated here. What if I have 30% of the R and 70% of the S? So here we are going to get a negative, let's say a negative 40 degrees angle. So 30 of the R here will form a racemic with 30 of the S here, remaining 40 of the S. So S dominates here and it will turn the plane polarized light to the right. So turn it to the right, giving us let's say a 40 degrees angle, which is positive. So now, after forming the racemic, what is left is the enantiomeric excess. Here, the enantiomeric excess is 40%, favoring the R. And here, the enantiomeric excess, is 40%, favoring the S, because S dominated here. And here, the enantiomeric excess is calculated as the specific rotation of the mixture over specific rotation of the pure sample, which is PS, pure sample. The specific rotation of vitamin B in water at 25 degrees Celsius is positive 90 degrees. A chemist prepared a mixture of vitamin B and its enantiomer, and this mixture had a specific rotation of positive 80 degrees. Calculate the enantiomeric excess of this mixture. So a pure vitamin B will have a specific rotation of positive 90 degrees. But a chemist preparing a mixture of vitamin B and its enantiomer, and this mixture had a specific rotation of 80 degrees. So E mix. This is the pure solution. So E mix is positive 80 degrees. And in enantiomeric excess, this should be multiplied by 100. Sorry about that. EE equal specific rotation of mixture over specific rotation of the pure sample. And the specific rotation of the mixture is 80. And that of the pure sample is 90, multiplied by 100%. And this gives us 88.89%. So the chemist is interested in separating vitamin B, but in the solution we have other enantiomer of vitamin B in the solution. That is why we are not getting 100%. If the solution should be purely only vitamin B without its enantiomer, the enantiomeric excess should give us 100%. So it means that some of the vitamin B has formed a racemic with the other enantiomer in the solution. So let's find the difference between this and that. So 100 minus 88.9 should give us 11.11%. And this 11.11% is the racemic mixture. And this racemic mixture was formed by vitamin B and its enantiomer. Vitamin B and its enantiomer. Let's represent this by E. So if we divide this 11.11 into 2 exactly, we are going to get 5.55% here. Use the calculator to do that. Yeah, 5.55% here. So 5.55% of the vitamin B and 5.55% of its enantiomer came together to form a racemic mixture of 11.11%. That is why the enantiomeric excess of the vitamin B itself is not 100%. So if we are looking at the total percentage of the vitamin B itself and not it in the solution, we are going to add this to the part that came together to form the racemic with the other enantiomer. So 88.89 plus 5.555, all in percentage. So total vitamin B in the solution is going to give us 94.445%. That is the total vitamin B in the solution. The specific rotation of ephedrine in ethanol at 25 degrees Celsius is minus 6.2. A chemist prepared a mixture of ephedrine and its enantiomer, and this mixture has a specific rotation of minus 5.9. Calculate the enantiomeric excess of the mixture and the total percentage of ephedrine. So at the beginning of the question, the specific rotation of ephedrine in ethanol at 20 degrees is this. So that should be the pure specific rotation of an ephedrine. So we are looking at E in enantiomeric excess, specific rotation of mixture over that of the pure. So now we've gotten to know that of the pure is minus 6.2 degrees. And a chemist prepared a mixture of ephedrine and enantiomer, and this mixture has a specific rotation of minus 5.9. So specific rotation of the mixture is minus 5.9. So evaluating this by 100% gives us 95.16%. We are not getting 100%. Why? But the question says that we should calculate the total percentage of ephedrine. This is not the total percentage of ephedrine. Ephedrine, if the solution should contain only ephedrine, then it should be 100%. But since this is not the total, it means something is happening. Some of the ephedrine has formed a racemic mixture with its enantiomer. So let's find the difference. So 100 minus 95.16 gives us 4.84%. So with this is the value of the racemic mixture that was formed, 4.84%. It means this value here has ephedrine and its enantiomer that came together to form a racemic mixture of 4.84%. So now let's say we divide this into 2 exactly, we get that of ephedrine and its enantiomer. So dividing it by 2 exactly gives us 2.42% and here 2.42%. It means that some of the ephedrine, 2.42 of the ephedrine and 2.42 of its enantiomer came together to form a racemic mixture of 4.84%. That's why we are not getting the percentage of the enantiomeric excess of ephedrine to be 100%. So the total percentage of ephedrine here is this value here plus 2.42. So 95.16 plus 2.42, all in percentage. That will give us 97.58%. So this is the total percentage of ephedrine. Found this video helpful? Kindly subscribe to my channel and give a thumbs up to this video for more educational content like this. You can also refer my channel to your friends. Thank you. Bye.